We are Team Mama, and this is our question and answering system.
This is the architecture diagram of our question and answering system. For the question generation aspect of our system, our input is the Wikipedia articles, which we first pre-processed. Then we generate questions such as auxiliary questions, as well as who, what, where questions. The next step is question selection, where we filter the questions we have selected through a grammar checker, and then we use cosine similarity to rank these questions. The output of this is our final questions. For our answering system, we are given a set of questions to answer as an input. We find the context that is relevant to the questions and then extract key phrases from the context. These key phrases are our output.
For the pre-processing, we did both manual pre-processing and used the NLTK package. For the manual pre-processing, we got rid of the references and titles from the input Wikipedia articles. We also wrote functions to remove commas, special characters, and stop words. We had a function that checked for correct spelling, and we also performed contraction mapping, where we expanded all the contractions. In terms of using the NLTK for pre-processing, we used the package to detect and split our sentences. We performed part-of-speech tagging and name entity recognition on our input. We also had a lemmatizing functions that lemmatized the words in our input text as we needed it for one of our question generation methods.
One type of manual question generation that we did involved using NLTK's name entity recognition system to identify people and locations. Then, using the dependency trees that NLTK generates, we were able to create questions about the name entities, mainly who and where questions. We also used Spacey's tokenizer to find auxiliary verbs and flip the sentence to generate binary questions. For example, Dempsey is a soccer player goes to, is Dempsey a soccer player?
Another method for generating questions was using the T5 transformer, specifically T5 question generator and T5 tokenizer. We used the model from PKE, the Python key phrase extraction package, to extract key phrases from our lemmatized input text. The models used were the single rank and text rank models, which are both graph-based. We removed any duplicate key phrases that were returned from these models and sorted the key phrases based on their average normalized rank. Then we performed sentence mapping on the key phrases to tokenize our input sentences. This allowed us to extract the sentences that contained our keywords. These sentences serve as the context from which our questions were generated. Then, using the T5 transformer question model and tokenizer, we generated more questions.
Since the manual question generation could occasionally create invalid questions, we used the package language tool Python to filter out questions that aren't grammatically correct. Then, in order to pick the best questions from those generated, we sorted them by their cosine similarity with respect to the article. If we found a sentence that had a cosine similarity of 0.2 or greater to the question, we kept the question. This results in only questions that have some relevant passage in the article. Then we picked the questions with the lowest cosine similarity of those remaining. We found this resulted in questions that had a good level of difficulty as they weren't too similar to the text.
To find answer context within the article, we used a combination of both cosine and Jacquard similarity. To find the cosine similarity, we turned the question and every sentence in the article into vector using scikit-learn's TF-IDF vectorizer, and then compared the question to every sentence. Only sentences with a similarity above 0.2 are relevant to the question. We found, however, that the cosine similarity had unreliable results, so we wanted to incorporate another form of comparison, for which we decided on Jacquard similarity. Jacquard similarity compares the words that occur in the question and the sentence. In order to make this even more focused, we ignored the 100 most common words in the English language. In order to combine the two similarities, we just took the product, which we found resulted in the most consistent results. In order to meet the conciseness requirement, we decided to detect binary questions, also known as yes or no questions. In order to answer these questions, we found their context the same as before and analyzed both the question and the context for negatives, mainly the word not and any contractions that contained it. For example, if we asked, is Clint Dempsey not a soccer player, and we find the context, Clint Dempsey is a soccer player, our system would respond no because of the mismatching negatives in the question and the context.
From the context found for each question, we used position rank and text rank models from the PKE package and the rake model from the rake NLTK package to extract key phrases and their rankings. We ignored all of the common words in the input text and didn't consider them as key phrases. This method didn't work quite as well as it didn't take into account what the question was actually asking. Using BERT and the auto tokenizer from the Transformers package, we created a pipeline that generates the key phrase with the highest ranked answer given the context and the question. The context is a sentence returned from the cosine and Jacquard similarity.
Currently, our system only considers one sentence at a time. However, to improve answering, it would be better to consider multiple sentences at the same time in order to use co-reference resolution. For example, consider this context. Mary was born on September 23rd. She is really good at playing the banjo. If our system was given the question, who is really good at playing the banjo, it would output she. Instead, we want to use co-reference resolution in order to answer Mary.